To hear any mention of the Winnie-the-Pooh books brings up images of simple, light-hearted characters that make us think of the joys of childhood again. Why in the world would something as ugly as a mathematical proof invade this land of simplicity and joy? And how could it be hidden? Wouldn't the darkness of something so ugly stand out like a strange alien being? Well, the chapter that contains the proof in question is pretty dark to begin with. It's in chapter 7 of the first book, where Kanga and Roo first appear. Rabbit, Pooh, and Piglet are very uncomfortable with the newcomers, because they were new and because Kanga had the strange ability to carry around a family member in her pocket. They decide if they can kidnap Baby Roo and hide him from his mother, Kanga, they can make the two promise to leave the forest and never come back. Yikes. Wow, that's dark. So where does the proof come in? The first thing to realize is that the Winnie-the-Pooh books were written by A. Milne, a man who had a degree in mathematics from Cambridge. So he had a strong mathematical background and knew how to draw up a proof. Second, he had a gift of making even dark things look innocent. So even though this chapter seems dark on the surface, the ignorance of the childlike characters trying to accomplish a kidnapping without any real desire for malice really takes away the dark undertones that would be inappropriate for a children's book. Since the uncomfortable characters don't have a clue how to perform the kidnapping, Rabbit comes up with a plan to capture Baby Roo, and Rabbit writes it down in a format similar to some mathematical proofs. Here's a copy of the plan that Rabbit writes. I'm not reading it all because it would be too tedious for the viewer. The viewer can just pause the video if necessary. Of course, all this translated into plain English is, if we can get Pooh to distract Kanga and switch small Baby Roo with small Piglet while she isn't paying attention, we can get away fast enough to capture Baby Roo. But how is Rabbit's plan like a mathematical proof? Well, mathematical proofs are built on things called axioms or postulates. These are statements understood to be true without requiring any justification and serve as the starting points for arguments. In Rabbit's plan, these are written down as general remarks or thoughts. Also, there are a lot of conditional and quantifier words spread throughout Rabbit's plan. These are words like any, never, except, if, then, because, so, not, and until. These are words frequently used in mathematical proofs. So now we're really starting to draw similarities between Rabbit's plan and a true mathematical proof. Another thing that would be helpful to get us to realize how this plan is a mathematical proof in disguise would be to code some of the statements as variables to make the logical connectors stand out more. So let's do that now. Here we've assigned the phrase Kanga runs the fastest to variable A, Kanga watches Roo to variable B, and so forth. Now that we have all the variables, we can translate Rabbit's plan as follows. Now we can sort the statements into a more fluid order, fill in some holes, and abbreviate into something called sentential logic. I learned sentential logic from Professor Nicholas Asher at the University of Texas at Austin. It's interesting to note that the university has a lot of A. Milne's original documents and correspondence stored in its Harry Ransom Center building. I've never seen those documents, though. I didn't know anything about Milne back when I was a student there. Here are some popular symbols used in sentential logic that we'll use for our proof. Using these symbols and converting our work so far into sentential logic, while shifting things around more efficiently, this is what we get. If this isn't a logical mathematical proof, then I don't know what is. Provided I didn't make any typos in this long chain of argument, it should be consistent enough for any mathematician to follow and agree that accepting the givens at the beginning leads to a true conclusion at the end that cannot be refuted. Most mathematical proofs are accepted without being converted specifically to sentential logic, but I think sentential logic proofs are the strongest kind. Of course, this doesn't prove that Rabbit's plan will work. It merely proves a plan is possible. Every time we show an event is in the set of possible events, we also keep in mind that that doesn't prove the event is in the set of guaranteed events. It's possible for Pooh to talk excitedly but Kanga to ignore it. It's possible for Kanga to not watch Roo but still detect the switch between Pooh and Piglet, perhaps if one makes a noise. It's possible that the switch happens but a head start doesn't because Kanga asks Rabbit where he's going. And it's possible that Rabbit gets a head start but is unable to get away because he trips on something. Some of these possible fails are more remote than others. It's interesting to note that even a simple plan like this, as we've just demonstrated, can be highly mathematical in nature, just disguised a bit more for brevity. It kind of gives you an idea why computer programming is becoming so powerful, since it can be used to model plans we make in everyday language by substituting precise mathematical logic. For anyone whose brain, like mine, is tired after all of that logical language conversion, I recommend doing like Pooh and reciting the poem Cottleston Pie to clear your head. Cottleston, Cottleston, Cottleston Pie, a fly can't bird, but a bird can fly. Ask me a riddle, and I reply, Cottleston, Cottleston, Cottleston Pie.